Okay, today we're going to be talking about the hybridization of orbitals. Hybridization is when orbitals combine to form hybrid orbitals. First we're going to talk about the CH3 molecule and its hybridization. Here's a picture of the hybridization. As you can see, there's only one bond between the carbons. This CH3 molecule hybridizes the 1s and 3p orbitals, making 4 sp3 orbitals around each carbon. This is the orbital diagram for the CH3 molecule. CH2. Not yet. As you can see, there are 4 sigma bonds, 2 holding the carbons together, and 4 sigma bonds per carbon. And then there are 2 holding the carbons together, and 1 holding each hydrogen to those carbons.
Here's a Lewis structure for CH2. CH2 hybridizes into 1s and 2p orbitals, making 3 sp2 orbitals around each carbon and 1 pi bond between each of the carbons. And this prevents the carbon from twisting and breaking. And here's an orbital diagram of the CH2. And as you can see, there is 1 pi bond on the top and bottom of each carbon, and there's 2 sigma bonds in between each carbon, and 1 sigma bond holding each of the hydrogens in place.
And the pi bonds are not as strong as the sigma bonds, which is why the bond energy required to break the bond is not the same as breaking 2 bonds. Here is the Lewis structure for CH.
As you can see, there is 1 hydrogen on each of the carbons with a triple bond in between the carbons, and this hybridizes into an sp orbital, and there's 2 sp orbitals in between each of the carbons, and 1 sp orbital holding on the hydrogen to the carbon, and there are 2 pi bonds on each of the carbons holding the carbons together.
One of the pi bonds is on the z-axis, so it's out front. We go to the dance now.
No?
No. This is how Mr. Shalednik taught us to remember where the pi bonds are at.